All right, so we are going to start with what we did on pre-stressed concrete. So today we want to look at the question which we posted some time ago. We have a post-tension concrete beam for a bridge. In that beam we have an anchorage recess of 0.15 meters from the end of the beam. And that concrete beam spans 20.35 meters. Now we've been given what we call the control points. Now control points are very essential in determining the losses along the beam. So we've been given 5 control points, control point 1, 2, 3, down to 5. So we have the first control point, which is at the edge of the beam, being a straight line. It is very essential the control point at the end of the beam to a certain distance of about 1.5 or less be taken as a straight line. So in this question we've been told that between control 1 and control point 1 and control point 2 is a straight line. And we also have control point 4 to 5 as also a straight line at the other end. Okay. Now we've been given the equation of a straight line, which is y is equals to mx k. So this is the equation we've been given. So this is what we intend to do, this equation. We also have the other part of the profile to be a parabola. So we have the equation of a parabola, standard equation of a parabola to be y is equals to as squared plus bs plus c. All right, now the coordinates on the profile at control point 1, 2, 3, 4, 5 are given respectively. We've been told these are the control points. Control point 1, we have control point 2, and we have control point 3, 4, and 5 respectively. All right, so these are the data for the control point. The figure in question is this. We have the straight portion, which is this particular portion down to 1. From this other right hand side, we have the straight portion terminating at 0.4. Okay, so we want to obtain the constant for the parabolic curve as well that of the straight line curve. Now take note, it is very essential you start up with this parabola, because we know that for the parabola we have the maximum turning point of the curve to be at this section, which is section 3. So we are expecting to have the maximum value at this point. Of course, if we measure the distance from the end down to this point, we have it to be 10.1175. okay, so that is what we have as the distance. So we are going to treat the whole of this section down to this point as a parabolic curve. Now so we look for this unknown. We look for m, k, a, b, and c in the various expressions, and also we have been asked to determine the coordinates and the slopes at the point on the profile at interval of 2 meters. So let's go over and see how we can work that out. Now we look for the solution. All right, so we look at how we can be able to work that out. The standard equation of a parabola is y is equal to as squared plus bx plus c. Okay, so remember for the cable point 2, for cable point, control point 2 rather, we have x to be 1.175, and then we have y to be 0.54. Okay, so these are the two points in that control point. We equally have control point 4, where we control point 3 rather, we have this control point 4, we have 19.175 and 0.54 as our control point 4.
All right, so we know that when x is 1.175, we have y to be equal to 0.54. So we substitute it into the expression 175 square of a, 1.175 square a plus 1.175 b plus c equal to 0.45. All right, so all we need to do is to simplify it. Once we simplify the expression, we have 1.380625a plus 1.175b plus c equal to 0.54. So that is the first equation we are going to deal with. Now we look at where s is equal to 10.175, another point along the parabolic curve. So we have that value to be 0.197. Okay, so we are going to substitute that same value of x is equal to 1.175. So we'll plug it in. We'll have 10.175 square a plus 10.175 b plus c is equal to 0.197. All right. So when we simplify that, we're going to have our equation number 2. Okay, remember we have 3 unknowns, so we need 3 equations. All right. Let me clean off this side. All right. So let's call here equation 1. Let's call this one equation 2. So we look for the third equation, which is equation number 3. So once we get equation 3, we can work it out to obtain the unknowns. Okay. So let's do it on this other side. All right. So simplifying that expression, we're going to have a 103.53a plus 10.175b plus c equal to 0.197. Okay, so once we've done this, we can call this our equation number 2. I think we need to reput it in rearrange it. So that is equation 2. So let's work on when we have x is equals to 19.175. So we can substitute it. The value for y is 0.54. So we'll do that. If we work that out, we're going to have 367.68a plus 19.175b. So we'll have these values. Okay, so once we obtain the values, we'll have the 3 equations we've gotten. We'll solve it using matrix. We'll obtain the values for A, we'll obtain the values for B, we'll obtain the value for C. So once we obtain the value for the 3 unknown, A, B, C, we can now link up this curve to our straight line portion. All right.
All right, so looking at the values we've obtained, we obtained pretty all the values we needed, A, B, C. So these are our value C. So now that we've gotten all the value, we need to write the expression for the parabola. So this is the equation of the parabola. We have 0.0042342945x squared minus 0.0861728x plus 0.6854. Okay, so these are the values we obtained from this particular equation. All right, so this represents the equation of this parabola. Now with this equation we can link this equation with the equation of a straight line, which the profile is expected to have a straight portion from this particular entry point. So if that is the case, we are saying that at this particular point here, so we are linking this part of the profile down to this control point 2. So at control point 2, we can begin to look at how the parabolic portion connects to the straight portion. So this portion will go into the recess of the beam. So now we know that wherever is the slope at control point 2, both for the straight line and for the parabola will be equal. So we have that at the back of our mind. So coming back to this point, we've written the expression, we know that change in the slope of the parabolic curve, which is this expression we have now, 0.0086172 minus 0.0086178. All right, that gives us the change, the change in the slope at that of the expression. Okay, so we can call that change to be zero, to obtain the maximum turning point of the curve, which is at section 2. So if we do that, we have the value at which we have the turning point. We can check it out. If we work that out, also we'll have 10.175. But now let's look for the value for the slope at these points. So we'll look at the value for the slope at 1.175. So if we work that out, substituting the value for x is equal to 1.175 into this expression of our slope, we're going to have the final value for slope at 1.17 meters from the support to be minus 0.086172. So this gives us the slope at control point 2. So we are saying that at control point 2, we have this as our slope at control point 2. Now, with respect to the straight line, this slope is the same. So if that is the case, we can rewrite the expression for the equation of a straight line so that we can obtain our intercept. So this becomes our slope. So it means that for equation of a straight line, we will have ms, we'll have ms plus k, where k represents our intercept. We've already known our ms, so we know what we need to obtain is our k, we know our x, we know our y. All right, so we just go and plug it into that expression so that we can just obtain the intercept in the vertical axis of the beam. All right, so I say for the straight line, for the straight portion between control point 1 and control point 2, the change in slope is this at control point 2. So we can substitute values for x. So when x is 0.45, we have when x is 1.175, we have our y to be 0.54. All right, our slope remains the same. So if that goes the same way, we will have to obtain our k. You discover that our k value for the intercept will be 0.902. So we can rewrite our expression for the straight line portion to be this. So we've been able to obtain the various unknown in this problem. Now, having obtained the various unknown, we'll go straight to obtaining the slope at various interval. So we obtain the slope at various intervals. Okay, so let's look into that.
All right, so we've already have the table for the x and y coordinate as well as the slope at interval of 2 meters. So we are going to get the coordinate. We'll have the x value at 2 meter interval. So let's make this table a little bit wider, 8.17, 10.175. Okay, we'll extend the table a little. All right, so we are going to enter the equation. The equation is y. Let's record the equation we have here. This equation. So we bring that equation. All right, so having written those equations, we have it on top of the table. So we are going to put the x and y coordinates of the expression uh, and fix in the value for the slope. 0.1.175 meters. We first of all have to differentiate the equation like we've done before to obtain the value for that slope. Of course, we have that slope as a minus 0.08116. Okay, so haven't gotten that slope, we need to fix in other datas. All right, so I also bring in the equation of the straight line. Y is equals to minus 0.081196 x plus 0.902. So we have that as equation of the straight portion. All right, so now having written that, we can equally bring out the slope expression for this particular uh, curve. Let's bring out the slope expression. We have our dy dx, which represent our slope. Once you are able to fill in the information, you can proceed to calculating the losses in the tendons. All right, so alternatively, we can also, in practical case, make use of the third degree polynomial curve. This has also been found to be very efficient in terms of losses. All right, so we can do that. So thank you very much for watching. I'll see you in our next class. Have a wonderful time.